Okay, good morning, everybody. Let's get started. Between now and the end of the semester, I will spend a few minutes at the beginning of most classes sort of throwing out some tips and tricks for various issues in PyroSim as they arise for final projects. Many of you are doing swarm robotics for your final project, or predator and prey, in which you have two robots running around in the same simulation. We talked a little bit last time about collision groups. So if you have a relatively complex simulation with multiple robots, each one made up of multiple parts, you also have an environment made up of multiple multiple objects. You want to control the collisions between them. We talked about that a little bit last time. I want to switch now and talk about issues that arise when you're trying to simulate more than one robot inside the same simulation. From PyroSim's point of view, PyroSim really doesn't know anything about robots. The only thing it knows about are objects, joints, sensors, motors, neurons, and synapses, right? So it's not too difficult to create multiple robots where you're creating those 6 elements for one robot and then for the next. On the PyroSim side of things, there may be one large collection of sensors and another large collection of motors spanning all the robots in your simulation. But as long as you're careful to wire up using synapses, sensor neurons to motor neurons inside the same robot and not create synapses from a sensor in one robot to a motor in another robot, you're okay. If you do, what kind of swarm do you have?
Centrally controlled.
Possibly. You have a sensor in one robot and connect it directly or indirectly with synapses to a motor in another robot.
One robot?
You've got maybe one robot. So you can, of course, attach multiple robots together. We will talk briefly towards the end of the semester about modular robots, where the modules can actually attach and detach from one another using magnets or other connection mechanisms. If you connect a sensor in one robot to a motor in another, you kind of have telepathy, right? The one robot knows what the other robot is experiencing. So just be careful when you're creating multiple robots in the simulation to make sure that you don't have telepathic robots and synapses are restricted to inside each robot. Okay, if you have multiple robots, now let's look at the evolutionary algorithm side. How do you go about evolving swarms of robots? There are different ways to do this depending on what you want your robots to do. So in certain swarms, the robots are cooperating. For example, you have 2 robots that are trying to lift and move an object that's too heavy or too large for any one robot to lift on its own. Or you have a competitive situation where one robot is a prey robot trying to run away from a predator robot, which is trying to approach the prey, and so forth. How do you go about setting up an evolutionary algorithm for this latter situation where you have competition between the robots inside the same simulation?
You could set up a success state for the predator robot if it catches the prey, and then a failure state for the prey robot if the predator catches it.
Possibly. So a success state for one if it succeeds and a failure for the other and vice versa. How do we go about evolving that situation?
Fitness functions. One for the prey robot, one for the predator.
Absolutely, right? So we could create different fitness functions for the predator and prey or whatever your competitors are. How would you organize your population? So at the moment you have one population. Most of you at the end of the phototaxis task, you have a population of n elements, and each element in that population is usually a vector that specifies the genotype for one robot. So we can make alterations to the fitness function. How might you go about alter the population structure?
You actually split it, just have 2 independent populations that interact.
Exactly. So the simplest way to do this when you have a competitive situation is, for example, create a population of predators and a population of prey. We spent a fair bit of time in one of the assignments going through and refactoring and organizing your code into hierarchical classes. You should at this point, I think, have a class called population. There's no reason why you can't have more than one instance of that class. So let's imagine now that each of these populations is of size n. So we have a total of 2n robots that are being stored in these two population objects. How do we evaluate these robots? Well, let's say we have a fitness function for our predators. We have a separate fitness function for our prey. How are you going to evaluate the fitness of each individual in these two populations?
I probably would simulate them against a random member of the other kind of populations as opposed to the current best one.
Okay.
Because you want to evolve them to deal with a variety of different situations from the other group, not just the best evolved.
Not the best of all. So we could, for example, pair up individuals from each population randomly, which would expose them to different situations. What else might we be able to do?
Compare them all against each other.
We could do all against all. So we could take, for example, the first predator and run n pyrosim simulations, either one after the other or in parallel. We take the ability of this predator against all the other prey, and how do we compute the fitness then for this one predator?
Average.
The average probably of how well it did at chasing each of these individual prey. And vice versa for the prey, right? Same thing. Okay. This is pretty exhaustive. It'll give us a pretty good estimate of the average ability of each predator and each prey. What's the drawback?
Do n-squared simulations.
We have to do n-squared simulations. Obviously, doing just one simulation takes a little while. This is going to become very computationally intensive. So we could randomly pair up individuals, which allows us to do just n simulations. But we get a pretty poor estimate, at least at any one generation, of how well a predator is. This predator might actually be pretty good, but if it gets unlucky and gets paired up with an excellent prey, we might get a misleadingly low fitness value for a predator.
What if we pair it against two, we pair it against the highest fitness opponent and then a random one?
Could do that. We could do 2 simulations per predator, once against the best prey and once against a random prey. Other ideas?
You do the average of the group.
Sorry?
So you evaluate the average fitness of the prey compared to the average fitness of the predator, and so then it kind of measures how well they do as a collective.
We could do that. Yeah, exactly. So there is no one right answer here, but as you can see, there are many different ways to do this. And you're basically trading off the ability of evolution to estimate the average ability of any one individual against the number of simulations you need to run to do so. Scott, question?
So one issue with what we're doing right now is that population is what controls spinning off the simulations. We have 2 populations, so you end up with some sort of something above population that says, hey, joint population, go do something.
You could do that. So in terms of the coding side, you could create a class above this called populations, plural, if you wanted.
It spins all the simulations, calls both populations, but builds one sim for both of them.
What you're usually doing is you're creating one simulation and then drawing one element from this population object.
Okay.
Drawing another element from this population object, dropping them both in the simulation, remembering which 2 you sent to the simulation, and when you get back sensor data, make sure you pull out sensor data for the predator and sensor data for the prey, compute the fitnesses for those 2, store them. So there's a fair bit more overhead when you're doing things in this way, but it's doable. Okay. What about collaborative swarm robotics? So let's keep this simple and assume that we're still sending 2 robots to the simulation per simulation. Let's imagine we want a pair of robots and they're going to try and collectively push an object. What's the fitness function and what changes might you need to make to the evolutionary algorithm to make this happen?
I mean, depending on what kind of controller setup you have, you're going to need to evaluate fitness differently.
You might need to evaluate fitness differently. How do we evaluate fitness differently in this case?
Would you sum the individual contributions of all the robots?
We could.
So like in order to get a fitness function as how the swarm did as a whole?
Okay, we could do that. So we could set up the situation that we just had, for example. We could have two populations. We draw individuals from both populations, put them in the same simulation, and see how well they cooperate together. We could, and then sum up the individual contributions of each robot when it's paired up with some random robot from the other population. Could do something like that.
Because all the robots are doing the same task, we would have one population, just select two individuals.
Could do that. So we may not need both populations. Maybe we have just one population and pick two individuals at random in the population. What is the simplest possible thing we could do from the point of view of making the least changes to your phototaxis code if we want to have two cooperating robots?
Make an individual be two robots.
Make an individual be two robots, exactly. So an individual has somewhere inside it a vector of synaptic weights. There's no reason why you can't send two copies of the exact same robot, and in each robot you set the weights to be exactly the same. So you have two clones that have exactly the same brains, the same set of synaptic weights inside of them. Will those two clones exhibit exactly the same behavior in the simulator?
No.
Why not?
They interact with each other.
They interact with each other, they interact with the world, right? So if you place those two robots at two different positions in the world, depending on what else exists in the environment, they may have different sensory inputs. And even though they have the same set of synaptic weights, they're obviously going to get different values arriving at the motor layer in the first time step, which means they're going to move differently, which means now they're really going to get different sensory input at the next time step, and so on, right? So for those of you that are doing collaborative swarms, I would suggest you start with this simplest case of assuming that an individual may be one or more robots and just send n clones. And then the fitness is how well the group of clones did, and that fitness value gets associated back with that one individual. Okay, just some ideas to think about if you're doing more than one robot in PyroSim. Any other questions or ideas in PyroSim that you'd like some help with? Question?
Actually, this is a little different than what we're talking about, but how do you move the camera around?
Aha, good question.
Figure out how to do that.
I think in the current version of PyroSim there is a way to do that, and I can't think of the command off the top of my head. If you send me an email, I will send a note back to Blackboard or the subreddit. Scott?
I'm controlling mine.
Oh, you are? What's the command? Do you remember?
In the actual spinning up the sim call, you can set the initial point and rotation.
So when you call start.
When you start sim.
When you start sim. Okay, so right, so there should be somewhere in there a set of arguments for, I think it's HPR and XYZ.
Yeah.
Okay, so XYZ is the position of the camera in the world. And HPR stands for heading, pan, and roll. So again, I forget what it is. One of these is heading, one of these is pan, and one of these is roll. So basically, where's the camera and where is it looking, right?
Pitch is the angle, peak the pitch.
That's it, thank you. Okay. Other questions?
Oh, I was just gonna add that you can
Yep.
also just change this with the mouse while you're running the simulation.
You can change it with the mouse, but if you'd like but often when you're building your simulation, you'd like it to open so you can see from a particular view. You can set it initially in is it the constructor or the start command? When you actually create.
It's start sim.
It's the start sim, okay.
Instantiate the sim, you put it with there. There
Okay,
are other.
so it's in the constructor.
You can control it on the fly also. You can set it to follow, which is, if you want some nausea, do that.
Okay, so
Follow
that's a
the
new
robot.
feature
And
I
when the
haven't seen
robot
yet.
jumps, the camera goes
You
away.
can do camera follow, yes, exactly, sure to induce nausea. Other questions? Yes?
So for assignment 10, I think it was, we started running things in parallel.
Correct.
Or assignment. Is that pretty much the limit in terms of running things in parallel with PyroSim? Is there any way for it to, because once you start adding 4 environments now, things really start to slow down. Is there a way?
Right. So that is a good question. So there is no way at the moment to parallelize an individual simulation, right? If you think about it, especially in terms of collisions, you have all these pairs of objects, and at any given moment, any pair of objects may be detected by the collision detector and needs to resolve it. There is a lot of work going on at the moment at Google and NVIDIA and some other companies to try and create GPU-based physics engines that are also differentiable so that you can use deep learning. And those, at least in theory, should be parallelizable down to the level of individual GPUs. They're getting there. It's not quite user-friendly yet, but in another year or two, we'll probably be there. So at least in terms of pyrosim, we cannot parallelize an individual simulation, but there's no reason why you can't start up multiple simulations in parallel. Depends on how powerful a machine you're running things on. The example we just talked about with the N predators and the N prey, if you do all against all, you have 2N simulations. If you try and run all 2N simulations at once, for most laptops, that's probably going to overwhelm things, and it would actually be slower to do them all in parallel than to do them all in sequence or to do a few in parallel. So you got to sort of play around with that a little bit depending on your own platform.
You briefly said that it wouldn't really make sense to ever have like these telepathic robots with synapse connections between them. But would that ever make sense? I mean, is there a situation that anyone has played around with, like, I don't know, like a queen bee kind of thing that would send a signal, or if members of the prey group like see a predator, like all the others would instantly get triggered to shift their behavior to get away from the predator?
So that's a good question. So we're coming back now to this issue about connecting a sensor in one robot to a motor in another. And I was sort of mentioning this tongue-in-cheek as telepathy, but of course all our modern machines do have telepathy. It's called Bluetooth or Wi-Fi. So there's no reason why you act, if that's what you're trying to simulate, if you're trying to simulate wireless communication among your swarm, there's an easy way to do it. Connect the sensor in one robot to neurons in another robot. If that's what you're simulating, then by all means, go ahead and do that. If you wanted to do something like centralized control, you could have one robot that's detecting something and sending signals from its sensors using synapses to all other robots. So you could simulate wireless centralized control, for sure. Yep. Other questions? Okay, so let's get back to lecture. Hopefully you're not tired of talking about the reality gap yet. I think we will probably finish our discussion of the reality gap today. Lecture 19 and 20 here are relatively short. And we're going to finish with two relatively recent publications. I think this was 2015. This one was just last year. Just to set these two projects in context, last week we talked about my contribution to this problem, the Resilient Machines project, in which we were evolving not just controllers in a simulator, but the simulators themselves. And as I showed you at the end of lecture 17, we can use this approach when something happens to the robot, like, for example, the loss of a leg. If we create a simulation by hand of an intact robot and the robot becomes damaged, we now have a greater gap between simulation and reality. So our approach to this problem was to not assume that we're going to create a simulation by hand. We're going to allow evolution to adapt the simulator based on the robot's current situation. Another approach that we're going to look at in a moment is to just create a vast archive of simulations. Train a whole bunch of different controllers for different situations beforehand, and then have them ready to go if something goes wrong, and hope that something in your archive will fit your current circumstances, right? Most of us spent the first few years of our lives playing and sort of doing this motor babbling that we talked about last time, exploring all the possible ways that we can interact with the world. And sometimes today, in our adult form, something might happen that's slightly unexpected. And although you may not have ever experienced that situation before, from a sensor motor perspective, it may be sufficiently familiar that you immediately have a way to handle it. right? Which is particularly useful if the situation is particularly dangerous. We don't want to always be trying when there's an unexpected situation. We don't always, at that moment, want to be trying different solutions to the problem because the vast majority of them may make things worse. So in a lot of circumstances, for an intelligent agent, regardless of whether it's a robot or an animal, it makes sense to play beforehand and build up an archive of contingency plans and have them ready to deploy quickly if something unexpected happens. So we're going to look at in a moment. And then we'll finish probably today looking at the first 3D printing of a robot that actually walks out of the printer. I realize now that the numbering scheme of the lectures is slightly off, but I think that's fine if you link directly from the schedule. Okay, so let's start with this publication that was published back in 2015. And as promised, this is an attempt to allow robots to adapt somewhat like animals do. This unfortunate canine here has 3 legs rather than 4, but has a perfectly happy life and is able to adapt and carry on no problem. So like you saw in the Resilient Machines project, we're going to look at this particular physical robot, which is going to suffer various kinds of damages. But in this case, when it detects that something has changed, it is not going to stop and update a simulation of itself and then generate a new controller. It's going to try as quickly as possible to recover from the damage. That's the game. Once something goes wrong, how quickly can this machine continue on with what it's supposed to be doing, which, as usual, is forward locomotion. Okay. So here's just a snapshot of what we're trying to do, and then we'll talk about the method to achieve this goal. We have a damaged robot that loses its front left leg here and turns to the left. That's the first trial. On the second trial, it's already starting to improve. And on the third trial, it's back to moving in a straight line forward. Okay, how can we create an algorithm that allows the robot to do that isn't sitting there and trying out a dozen or 100 things before actually adapting? Okay. The overall algorithm that we're going to look at today is called intelligent trial and error. It's going to pick what to do very carefully. And we're going to break this IT&E algorithm down into different parts. IT&E contains within it an evolutionary algorithm, but then it has some additional algorithmic components to it. So let's look at the evolutionary algorithm that sits inside IT&E. The evolutionary algorithm that sits inside of IT&E is called map elites. This is a common evolutionary algorithm out there at the moment. It's sort of state of the art. As you're going to see in a moment, it's going to keep the elites around. We're going to have a population of controllers, as we usually do. We're going to keep these elites around, but we're going to embed them not in a population. We're going to embed them in a map. So each individual solution is going to have a position in this map. Okay, let's have a look at how this works. Here is a sample controller that they're evolving, as you can see on the simulated hexapod. So we're going to start, as usual, by training some controllers in simulation. In this case, they were asking not just for controllers that would maximize the fitness function, which was fast forward travel. They're also going to encourage the population of solutions to generate diverse solutions. So last lecture, we talked a little bit about diversity. So we're going to look for controllers that cause the robot to move quickly, but also to move in as many different ways as possible. And there are different ways that we can measure diversity. Like we saw last time, we're going to do that by looking at different features of the phenotype, not the genotype. So we're going to look at the phenotype, or the behavior, and we're going to look for different behaviors. The underlying set of synaptic weights, which is the genotype, that we don't care about too much. We don't care how diverse one set of synaptic weights is from another one. It's just diversity. And the kind of diversity they're going to look for is they're going to look at each of the 6 legs of the robot and ask, what's the fraction of time that the robot spends using those 6 legs? So if there's one controller in which the hexapod kind of rears up from behind and lifts up its front 2 legs, and those 2 legs rarely, if ever, touch the ground, that's going to be very different from another controller, which causes the robot to tilt forward, and it rarely uses its back 2 legs. Those 2 hexapods may both travel exactly the same distance, but they do so in a different way. Okay, so let's have a look at a few of these gaits. So this one here, the middle left leg, as you can see here, is going to spend very little amounts of time on the ground and manages to travel quite quickly. In this case now, it's going to be the front left leg that rarely is in contact with the ground relative to the other 5 legs. Here's an example in which 2 of the 6 legs are rarely used. Nice thing about a hexapod is you got plenty of legs to spare. You don't necessarily need to use all of them. In the genetic algorithm in particular, as you've probably seen in implementing your assignments, the genetic algorithm quickly loses diversity, and you often have a population of highly fit solutions at the end, but they're all very similar to one another, which is not ideal. What we usually want is a population of high fitness controllers, but that those controllers produce very different behavior. So one of the open problems in evolutionary algorithms is how do we maintain performance and diversity at the same time? That's what the map elites algorithm is designed to do. And I think you can watch the rest of these gates at your leisure. Okay. So how do we go about creating these very diverse behaviors? I'm going to talk about that first, and then I'll come back to talk about the overall intelligent trial and error algorithm. So I'm going to skip around the slides here a little bit. The first thing we're going to do is what we always do, start by creating some random controllers. And those random controllers exist in a very high-dimensional search space or fitness landscape, right? And obviously the authors of this paper also cannot draw in higher than 3 dimensions. They're trying to draw in 4 dimensions here with the hypercube. Remember that if we have n synaptic weights in our robot, we have a fitness landscape that has how many dimensions? Not quite n, close. We have n individual synaptic weights that we're trying to optimize. N plus 1, right? So if you think about any one vector of n synaptic weights as existing in a high-dimensional space, the horizontal position of that point in the high-dimensional space is where it sits in those n horizontal dimensions. If we have only 2 synaptic weights, then you can imagine x and y, right? And then the third dimension, the z, is the fitness produced by those pair of synaptic weights when we run it on the simulated or the real robot, right? So I'm going to elaborate this cartoon as we go, which is going to outline this whole algorithm, but we're starting hopefully with something that's a little bit familiar to you. We create a controller at random, and it exists somewhere in this high-dimensional space. If we run that controller on the simulated hexapod, we have the n plus 1th coordinate in this n plus 1th dimensional space. So far, so good? Okay. We create a bunch of these to start with, And they exist in this high dimensional space. And the first thing we're going to do is to remap these points down from this high dimensional space to a lower dimensional space described by behavior now. So the fitness landscape, the position of any one point is dictated by the genotype, the values of the n synaptic weights. The position of the exact same controller in this lower dimensional space, the position of that point is now dictated by the phenotype or the behavior. Okay. Again, hard to draw in high dimensions. So for the sake of simplicity, we're going to assume in the cartoon here that the behavior space only has 2 dimensions. Let's think about this. Let's throw away the hexapod for a moment and imagine instead that we're evolving controllers for a biped. So we have 2 legs. We can look at both legs, and as the biped is moving around with a given controller, we can record the fraction of time during which any one foot is on the ground, right? If it hops on one right leg, then the left leg spends 0% of the time on the ground, and the right leg spends 50% of its time on the ground. If the biped shuffles and never takes either foot off the ground, then both feet spend 100% of time on the ground, and so on. As you can see, in the case of the biped, we have 2 numbers, two floating point values that describe the behavior produced by that controller. Right? If we take that percent of time and scale it down to a number that ranges between 0 and 1, you can now think about this 2-dimensional plane where any controller produces behavior in the biped, and the fraction of time those 2 feet on the ground become the x and y coordinate for that controller. And we drop that controller at that point in this 2-dimensional space. And we then color that point with a warm color, or a cool color. What do you think the color of the pixel in this low-dimensional, this 2D behavioral space represents? How well they did, exactly. So hot colors are going to represent high fitness or fast movement, and cool colors represent controllers that produce little or no motion in the robot. So far, so good? Okay, now let's throw away the biped and bring back the hexapod. What's the dimensionality of the behavioral space? 6 dimensions, and we're going to use the 7th dimension as the color, right? Yeah, exactly. So we're going from usually the hexapod, I don't know how many synaptic weights there are in this case, probably 100, on the order of 100 or 200. So we have a very high high-dimensional fitness landscape, and we're boiling it down to only 6 dimensions, which we can't draw very well, or can we? The authors spent a fair bit of time trying to come up with a way to visualize high-dimensional space in a 2-dimensional image. I mentioned that the IT and E algorithm, the intelligent trial and error algorithm, has this evolutionary algorithm inside of it called map elites. This is the map. The map is 6 dimensions. And at each position in the 6-dimensional space, there lives a controller, which is the controller that causes that robot to move, the hexapod to move in such a way that the 6 legs spend that fraction of time on the ground. Okay, before we talk about this picture in and of itself, let's try and run the map elites algorithm in our head. We create one random controller. We run it on the simulated hexapod, and we record the fraction of time that each of the 6 legs spends on the ground, which gives us back 6 numbers, which give us an address in 6-dimensional space. We go to that address in the 6-dimensional map, place the controller at that point, and color that point based on how far the robot moves.
So you're measuring the amount of time the leg spent on the ground and then relating it to how far the robot moves, but that's necessarily not true if it's just jumping.
Right, so what happens if it's stepping up and down in place? right? So imagine in that case that all 6 legs spend on average about half the time on the ground, which gives us an address in 6-dimensional space, 0.5, 0.5, 0.5, and so on. We go to that point, we drop that controller at that point in the map, and it got 0 fitness, so we put a blue pixel there, the coldest possible color. So far, so good? Okay. We've only evaluated one controller, so we take that one random controller, make a copy of it, mutate it, evaluate it on the hexapod, and if that new controller causes the hexapod to move in a different way, we're going to get a different address in 6-dimensional space. Right? The 6 legs will probably spend different fractions of time on the ground during that simulation. So we go to that different address in 6-dimensional space, drop that controller at that position, record the fitness, and continue. If you now run the Map Elite's algorithm forward in your head, you can imagine more and more points that are being dropped inside this 6-dimensional space with different colors. Okay. Now we're equipped to try and handle this picture. If you look at the long axis here, so this y and this x, these correspond to the fraction of time that the first and the second leg, the front left and the front right leg, spend on the ground. So we get our general position in terms of x and y, and that takes us, for example, let's say here. We now zoom in on this small grid. We take this range of values. We haven't figured out where to put this point yet. And we now look at the fraction of time that the third and the fourth leg spent on the ground. And we take this smaller inset pair of axes and treat them as axes that range between 0 and 1. Take the fraction of time that the third and fourth leg spent on the ground, find our position inside this inset axis. Takes us, let's say, for example, up here, which takes us into a third pair of inset axes, which are very, very small. We rescale those to 0 and 1. We take the fraction of time that the fifth and the sixth leg spent on the ground, the back 2 legs, and that gives us a position in space to drop this controller. So we're dropping it into 2-dimensional space. It's a warped picture of the higher 6-dimensional space, and we're kind of cheating a little bit, but it gives us a general way to visualize more or less what's happening in 6-dimensional space. Scott.
So as you run through all these controllers, you might get a second controller that has the exact same proportions. Do you only keep the highest one?
Good question. I've been intentionally hiding that fact for a moment.
I didn't ask you.
Okay, we're almost there. I want to make sure that we get the picture, literally get the picture here. Okay, so if you stare at this picture very carefully, you can see that in 6 dimensions, there are certain places, there are certain neighborhoods of fast-moving robots and other behavior and other neighborhoods with slow-moving robots. You'll also notice there are certain neighborhoods with white pixels. What do you think the white pixels represent?
Untested areas.
Untested areas. So as the Map Elite's algorithm is running, and at this point, each pixel corresponds to an individual controller. So Map Elite's has probably run through tens of thousands or hundreds of thousands of controllers at this point. But there are still some places that we haven't reached. We haven't found controllers that cause the robot to spend that amount of time on the ground. There is one neighborhood in particular, one point in this 6-dimensional space that is going to be impossible to find a controller to fit within. What is that point?
No feet on ground ever.
No feet on the ground ever, which is the 6-dimensional address 0000000, which, not surprisingly, is right down here, right? It's empty. And other points nearby are also empty, right? Very difficult to get all 6 legs off the ground for the vast majority of the time. Okay, as Scott mentioned, as we continue running this algorithm, periodically when we're evaluating a new controller, it ends up having the same address as a controller that's already been placed at that address. What do you think you do when you have a collision between two controllers? One that's already there and one that is trying to occupy the same address.
Take the better one.
Take the better one, right? We're back to our hill climber. You throw away the one with lowest fitness, and whichever of the two had the highest fitness goes into that slot. That's the map elite algorithm. So far, so good? It's actually, although it sounds complicated at first, not that difficult to code up. And it has this nice property of keeping around lots of solutions that have very different behaviors, right? We can visit this neighborhood out here, which corresponds to hexapods that shuffle along the ground. All 6 legs are on the ground. We can visit here where maybe the front 2 legs are not used very often. Down here, the back 2 legs are not used very often. We have a wide diversity of solutions for our undamaged robot. Why do you think the authors used the map elites algorithm inside this intelligent trial and error algorithm, which they're about to run on the undamaged or possibly damaged hexapod?
As soon as you lose a leg, you can just cut those. Go to the section of your map that has very little use of that leg.
If you lose your front left leg, somewhere in here you have a controller that has relatively high fitness, hopefully, that never uses the front left leg, right? It's in here somewhere, but where to find it is tricky. Because we're assuming, again, like in the Resilient Machines project, the robot doesn't know. It doesn't know that it's missing its front left leg. It doesn't have pain receptors. It doesn't have a camera. It can't see its own body. So it's going to have to find in this space the controller that allows it to recover from damage, even when it doesn't know where that damage is. The map elites algorithm helps us to get part of the way by hopefully having a sufficiently diverse palette of solutions to cover any possible contingency, or most possible contingencies. But the problem is going to be to find the one that you need when something happens. So let's carry on with this cartoon here. So we now understand our high-dimensional genotypic search space. This is the fitness landscape. We have this lower dimensional 6D map that contains very diverse controllers. We're going to introduce 1/3 space here, and this is our confidence space. In this cartoon, it's 2D, but I want you to imagine that it's 6 dimensions, so that every point in the 6D behavioral space has a corresponding point in the 6-dimensional confidence space. We're assuming at this point in the method we've trained a whole bunch of controllers on the simulated robot. We haven't tried any of them on the physical robot yet. And you can see that the confidence space is uniformly painted with cold colors. What does that mean? All those hints taken together should give you an idea about confidence about what? Crossing the reality gap, right? So each point here, the value at that point represents the confidence that the IT and E algorithm has about how well that controller will transfer from simulation to reality. Okay, let's play the game that we played before last time. Which controller are you going to send to the physical hexapod first?
The best one.
The best one, right? So we go back down to our behavioral space and we find the point that has the hottest color, which happens to be here. And we transfer it to the damaged robot. The robot doesn't know it's damaged, but it is. And we update both the behavioral space and the confidence space. So let's start with the confidence space. You'll notice that the position of that particular controller in confidence space has now gone from a cold color to a very hot color. What does that mean?
It crossed
Not that it crossed the reality gap well.
You know how it behaves.
We know how it crossed the gap, right? We just crossed the gap. We know how far the simulated robot moved, and we'll assume that we know how far the physical robot moved, and the difference between those two displacements, we know it. We have that number. We know exactly how well that particular controller crosses the gap. To know how well it did, we go back down here to the behavioral space, and we can see that we've now cooled the pixel in the behavioral space. So this is a little bit confusing because the color of the pixels in the behavioral space are, in some cases, the fitness of the simulated robot, and now, at least at that point, it's the behavior of the physical robot. We've cooled that down because we now know how these transfer. So cool colors here mean these controllers might work well on the simulated robot, but to the best of our knowledge, they don't work well in reality. So we're just going to cool the colors in this neighborhood. We're going to assume these controllers don't displace the physical robot well. Question?
So the confidence level, when there's now hot colors, that signifies that it has transferred.
It has the hot colors in the confidence space represent high confidence. High confidence. So the algorithm knows with confidence how well or how poorly things transfer from simulation to reality at that point. Not how well they transferred, but confidence about how they transferred.
Confidence on the graph below it.
Confidence on the graph below it. Exactly. That's a good way to think about it. So down here, we've painted this green. And if we go to the same point in confidence space, the confidence space says, I'm confident that the point in behavioral space is green. It's not so good. This neighborhood is not so good. There's also green over here, which says these don't transfer very well. But if we go up to the confidence space, the confidence point corresponding to that green neighborhood says, I'm not so confident that it actually is green. These slow-moving controllers on the simulated robot, for all I know, they might actually transfer well to reality. You might get a hot color in the physical robot. They might actually get the physical robot to travel faster than I saw them do in simulation. Make sense? So this is a common confusion about this algorithm. The confidence level is not how well things transfer to reality, how confident the algorithm is about which neighborhoods or which controllers transfer, how they will transfer from simulation to reality. A confidence of 0 says, I don't know. You send that to reality, the physical hexapod may not move at all, or it may move at the speed of light. I have absolutely no idea whatsoever. Here, in this cartoon, right at the hottest point in the confidence level, it's the hottest possible color. Confidence equals 1. It says, I know exactly how well that controller will transfer to reality because I just transferred it to reality. I know. I have that number. Now, if you want to know how well or how poorly, go back down to the behavioral space.
Does this metric of how well something transfers to reality include how well it's going to perform in reality, or just the correspondence?
It's different in different parts in the space, right? So over here, the information we have is just how far the robot traveled in simulation. Over here, the color is now how well it did in reality. So the best way to think about this space is just behavior, right? What is the quality of behavior? What is the speed of travel of the robot at this point in the behavioral space? It may be speed of travel of the simulated robot or the physical robot, depending on where you are in the space. It's also a little bit confusing.
So because the area is red in C and then is green in D, that shows that it works in simulation but not in reality?
It's now that it's green here, it just says it doesn't work, period, right? Whatever was there in simulation is really not that important because we've transferred it to reality. If it doesn't work, who cares what it was in simulation? The green around here just means avoid this area. In this green region, I'm confident things don't work. If you want to cross the gap, go somewhere else. That's what that means.
So over time, if the confidence level is then affecting the performance level, wouldn't over time the confidence level just completely go red? Because then it just
Yep.
You've tested every point.
When you've tested every point, eventually the confidence level will be uniformly red. It's sure about everything. If you did test every point, what can you tell me about the colors in the behavioral space? Are they going to be all red as well?
They'll probably shift to greener.
They'll be greener because most things don't transfer very well, but they'll be different colors still, right? Certain controllers will transfer better than others.
So, you test a point and it, let's say, doesn't transfer well, you paint the neighborhood green. Can you define neighborhood?
Exactly. So again, I've been intentionally leaving off this issue about the neighborhood, but as you can see in this picture here, we're painting high confidence at exactly the point of the transferred controller, but we are also painting points nearby, right? And if you look at this carefully, there's actually exponential decay, and there's different ways you can do this. But the assumption here is that this particular controller, which did not transfer very well, controllers very nearby in behavioral space also will not transfer very well. And I'm pretty confident about that. There's orange at that point in the confidence space. We didn't actually transfer that second controller, but that second controller is very near the controller that I did transfer, and that one transferred poorly. So I think the nearby controller probably won't transfer very well as well.
Did they use like previous experiments to get like how far you should decay out? Or something
That's a
like
good
that?
question. You have to go look at the paper itself. I'm not sure how detailed the discussion is of how they actually defined the neighborhood. But I think the general intuition makes sense, right? A controller that is nearby in behavioral space means that that nearby controller causes similar behavior. If that point causes the left front leg to spend little amounts of time on the ground, then a neighboring point in behavioral space also causes the front left leg to spend relatively little amounts of time on the ground, right? It's probably a pretty good assumption in general. There may be places in the map where that assumption holds up not as well.
And if you have another point that you sent to the reality and then those little like waves overlap, would that increase the color of it, or would it just stay the same?
Exactly. So what do we do is we start to transfer more controllers, right? So let's carry on now, unless there's other questions. So far, so good? Okay, so at this point, we are now pretty confident about this small neighborhood in this vast six-dimensional universe. Where do we go next? Next highest point, right? That's kind of giving it away here. We go to some other red region, right? Which says, at least according to the simulation, that causes the simulated hexapod to move quickly. But again, if we go up from that point into confidence space says, I don't know. Transfer that one across, and now confidence goes up in that neighborhood because we've transferred a controller in that neighborhood. And in that case, it also did not transfer very well. And we take those two new values, one in confidence space and one in behavioral space, and bleed that value into neighboring regions. We mix that value with a smaller and smaller weight as we move away from that point. Right? If you think about this as ripples going out from a stone thrown into a pond, ripples coming out from one behavior may come up against ripples emanating from another region. And that can happen in both confidence space and behavioral space. We just mix those values together, right? So if we have blue in here and we have hot coming down from here, we might mix them together and get green,
So
something in the middle.
Just like real waves, like they would just add.
Like real waves, you get positive and negative interference. So if you have waves of hot color coming out from a hot point, Those are like two waves hitting, and the where they meet is positive interference. You get a higher wave. You might get even hotter color at where they interact versus where they're flowing from. If you get one wave and one trough, red and blue that collide, you might paint that pixel green at that position.
But you're not going to have two low values coming together to make a higher value.
Exactly, right? Too low means stay low, exactly. So far, so good? Okay, so we got relatively unlucky, at least in this cartoon, with our two robots that we sent, but we can see that this green is spreading through behavioral space, right? We're depressing different neighborhoods and pushing the trials towards the remaining hot regions. And you might get lucky. So around here, there may be a controller that actually does cross the gap pretty well. So we retain our hot color here. We've sent it to reality and it's hot. And we also increase the confidence in that neighborhood. So we warm the pixels in confidence space around the same place. Assuming that happens, where do you think the IT&E algorithm will go next to find another controller to send it to the physical robot? We now have two regions, one in the behavioral space and one in the confidence space, that are both warm. We probably won't go over here where there may be slow-moving simulated controllers and high confidence that they won't transfer well to reality. And vice versa, we probably won't go to high confidence regions, low confidence regions that have hot colors in the behavioral space.
Maybe the next highest performance that you don't have 100% confident on, but that's not too similar.
Exactly. So the way that the IT&E algorithm really selects which controller to send next is the maximum of the products of each confidence value and each behavioral value. So each point in behavioral space is multiplied by its corresponding value in the confidence space. Confidence ranges between 0 and 1. 0 confidence, I don't know how well it'll transfer. Confidence of 1, I know exactly how well this controller will transfer. And we also have fitness values down here, which are also always positive. Distance traveled by the robot. So we're multiplying pairs of positive values together, and across this 6-dimensional space, we're now going to get a 6-dimensional space filled with pairwise products. The confidence value multiplied by the behavioral value. And we just look at that product space, if you like, and we pick the highest value in that 6-dimensional space. And wherever that highest value is, we take that 6-dimensional address and pull the controller out, and that's the one we send to the physical robot. Intuitively, we always want to send the one that has high fitness and high confidence.
So would there ever be a case where you're going to be kind of like the algorithm's just going to evaluate every single possible thing in a population before it explores like some other population that's not quite as high confidence?
Possibly, but because of this washing effect, you're usually jumping around a fair bit. Right? So in this cartoon here, we've just transferred across something that crossed the gap pretty well. So it's a hot color, but it's probably not the hottest color in behavioral space, because simulations are kind of optimistic, right? So it's high, but maybe medium. Confidence is maximal. It's at 1, because that controller was just transferred. There is probably somewhere else with even hotter colors. They're probably nearby, and not as high confidence levels that have a higher product. So we're going to go to that. The IT&E algorithm is going to go there and send that controller across.
Just one more time.
Sure.
Could you explain how the confidence level is determined?
Okay. So we have a simulated robot here, and it travels X units away from the origin. We take that controller, we send it to reality, and the physical robot travels y units away from the origin in reality. We take x minus y and the difference between those two displacements. That's the new value that goes into the behavioral space. Let's say the physical robot traveled half as far as the simulated robot did. So that's a medium temperature color. It crossed the gap so-so, 50%. So we put a medium temperature value at that point. The value that we put in the confidence space is 1, because the algorithm knows exactly the difference in displacement between the simulated robot and the physical robot. Imagine there is a pixel that is next to that pixel that we just transferred in confidence space and behavioral space. The confidence of that neighboring pixel might be 0.95. It says, I don't know about my controller, but it's very, very similar to the one you just sent. So I'm pretty confident that it's going to be about 50% transferal success, because that's just about what happened with the one that I just sent.
So the point we test is always going to be 1, and then fan out.
In confidence space, the point we always transfer is always going to be 1. Maximal confidence about how well it transfers. Neighboring points, near 1. We're assuming that similar controllers transfer similarly well from simulation to reality. So far, so good? Okay. Okay, so let's see how well the algorithm actually did. So here are 6 different damage scenarios that they looked at C1 through C6. C1 is no damage. We want the robot to still work when it's undamaged. Lose half of the front left leg. The middle right leg is permanently bent. It's hit a rock and the metal has bent, for example. Here we have an entirely missing leg, 2 entirely missing legs, and in this case we've given the robot a little crutch here, or a wooden leg. Seems like kind of an odd thing to do. I think I mentioned this last week. NASA's worried about their legged rovers where a wheel breaks off or a leg breaks off, or it steps in mud or regolith or something else, and now the leg is actually heavier than it was before. These are all obviously changes to not just the shape, but the mass distribution of the robot as well. Okay? Okay, how well did the algorithm do? Let's have a look at some results. So we've got the 6 damage scenarios down here, and each of the yellow stars represents how well the robot did on the very first trial. So in the case of the undamaged robot, the height of the height of the star represents the speed of travel of the robot, and you can see that in C1, the undamaged case, the robot travels a lot faster than the other 5 damage scenarios. So we take all of these simulations, and in the simulations, the robot is undamaged. The IT&E algorithm gives us one of those controllers to try on the undamaged physical robot, and it travels this far. Or we take that archive and IT&E sends us a controller and we send it to the physical damaged robot, and not surprisingly, it barely travels at all. So far, so good? Okay. After a few transferals, we let the IT&E algorithm run while it's sending controllers, and in between sending controllers, it's updating the behavioral and confidence spaces, and sends 1, 2, 3, 4, 5, maybe half a dozen controllers. And after sending just a few controllers, now the robot is traveling on average this far. You'll notice that in most cases, or in all cases, the purple bars are well above the stars, representing that even after half a dozen trials, the robot is speeding up again, even in the damaged case. And in some cases, it's going from basically no motion to more or less the mean speed of the original undamaged robot. So C2, as you can see here, is it's missing half of the left front leg. What controllers do you think are running here on the C2 robot that are enabling it to travel almost as fast as the original undamaged robot?
Where left front leg does not.
Presumably, it seems to be working, and it's probably a pretty good guess that the IT&E algorithm has moved into the neighborhood in six-dimensional space, and in that neighborhood exist controllers that don't use the front left leg, probably. Right? Okay. Even in very severe situations like C4, where there's a completely missing leg, or C5, where 2 of the 6 legs are missing. These are pretty catastrophic failures from a robotics point of view. We're getting controllers that maybe don't travel quite as fast as the undamaged robot, but not bad. Okay. You'll notice that there were 2 additional experiments they did over here with just C1 and C3 using an alternate descriptor. What do you think they mean by descriptor, alternate descriptor?
Different way for the robot to identify its movement.
Exactly, a different way for the robot to self-identify its way of moving. So the descriptor over here was what's the fraction of time that each of the 6 legs spends on the ground. That's kind of arbitrary. We could come up with a different set of descriptors. What's the average height of the robot as it travels? What is the change in horizontal orientation of the robot as it travels? We could come up with different behavioral descriptors. And they wanted to just show that their algorithm with different descriptors still allows the robot to recover functionality with just a few trials after damage, at least in the case of these different descriptors. So their results are not dependent on carefully choosing how to describe the behavior of the robot.
What was the star again? The initial...
Star is we take the physical undamaged robot, we take our IT&E algorithm, which is armed with all of those controllers, has 0 confidence about how all of them transfer, and run the algorithm for a couple of trials. I'm sorry, let me take that back. The IT&E algorithm takes the best controller according to the simulator. So we pick the hottest pixel in behavioral space, and confidence space is all uniformly cold, right? Send that one controller across, and that causes the physical undamaged robot to travel this far. The star over here is we reset the IT&E algorithm. It's filled with controllers that have been evaluated on the simulator. We reset the confidence level to be uniformly cold, and the behavioral space, it's all the predictions of how fast it's all the speed of travel of the simulated robot, and send the first controller from the IT&E algorithm to the physical robot. Surprise, surprise. We're trying to transfer a controller that worked well for the simulated undamaged robot to a physical damaged robot. Doesn't transfer very well at all. Okay. As I mentioned, the goal in this particular project was to allow the robot, like animals, to recover very quickly after something unexpected happens. So they're plotting the same data down here for the same set of experiments, but they're plotting the average amount of time it took to get to these speeds. So most of these speeds are not bad. They're about on par with the speed of the undamaged physical robot. And it took only 3 or 4 or 5 transferals, which took in total just a couple of minutes. So this is the main advantage of this algorithm compared to the Resilient Machines project that I described last week. Our algorithm is able to adapt a simulation that reflects the situation of the robot, but it takes a while. We have to evolve these simulators, send things back and forth across the gap. This one never changes the simulation, right? We have this simulated undamaged robot, and we have a vast library that we can rapidly draw from. and try and quickly narrow in on neighborhoods of controllers that transfer well. So we get speed here at the cost of knowledge. If you were to ask the IT&E algorithm what's wrong with the robot, it can't tell you. The only thing the IT&E algorithm can tell you is that controllers in which the robot does not use its front left leg is working well. So it kind of indirectly knows what the situation. There's probably something up with the front left leg. Question?
What would happen if just the touch sensor was, kind of destroyed if the leg was fine? Wouldn't it still think it's not on the ground?
That is the biggest nightmare of roboticists or mechanical engineers impossible. The worst possible failure is a sensor, right? When the check engine light comes on in your car, is your engine in trouble or is the check engine light detector in trouble? You do not know. You can't disambiguate between those two situations. It is one of the scariest things about robotics. And in this case, they did not test failure of a sensor, right? Generally, you hope that a complex machine like a planetary rover has enough sensors where it's sort of a vote, right? They can work amongst themselves. If one of them seems to be giving a signal, the others can say, don't ignore that sensor, it's doing something strange. They can override it. So it's interesting to think about how you might adapt this algorithm to incorporate that ability of sensors to override a misbehaving sensor.
Could you combine this controller selection with the resilient machine self-modeling to make a robot that doesn't need its sensors?
Possibly. So maybe you could go back and when you update the confidence space and the behavioral space, you also go back and update the simulator. You might be able to combine these. That's an interesting idea. Question?
When does the robot know when to run these trials?
How does it know when to run them? It just runs them all the time.
Okay.
So the robot just does its thing, and every 10 seconds it stops and asks for the best one. If the confidence space is uniformly warm, then it will usually get back the exact same controller it was just using. Right? That's the other nice thing about this algorithm is it doesn't need to be an explicit stop criteria.
So at the same time, would it make sense to, as it's going, constantly monitor its walking speed and fade the confidence level if it detects that it's not walking as fast as it had been, and then switch to a new controller dynamically?
Absolutely. So as it's moving, if it starts to slow down, then that point in behavioral space starts to cool off, which means the next time it asks for a controller, the next time it pauses, let's say we pause every 10 seconds, next time it pauses, it may get a controller from a different part of the space. The algorithm will do what you just described automatically. Okay, we got 2 more minutes left, so let's just carry on. We just looked at the results here. If you go and look at this paper, they also looked at a completely different robot, which in this case was an arm hand setup where the arm and hand is trying to pick balls out of a can. And they looked at 3 different damage scenarios for the robot arm. In one case, one segment became permanently stuck at 45 degrees, could no longer move. And in some other cases, a joint had a permanent offset. So it still was able to rotate, but when you asked for 30 degrees, it gave you 75 degrees. It had this permanent offset. These are common situations in articulated robotics. And in this case, within a few trials, I don't have the other plot here, I'm sorry. The arm was able to recover the ability to grasp objects in the bin and pluck them out of the bin in less than 30 seconds. So I think there was about 2 or 3 trials between the IT&E algorithm and the physical arm before it could, again, do what it's supposed to be doing. So a very rapid algorithm. Okay, we got 1 minute left, so I will show you the sort of summary video here, now that you know how this algorithm works. And I will speed it up because we're short on time. Here's the map being created. and placed in the behavioral space. Here's the undamaged robot. Damage. First transferal. Second transferal. Doesn't do very well. That point in the space is going to cool off. Goes to a different part of the space. That doesn't work. That part of the space cools off. And you can see it's found a neighborhood of controllers that transfer well. Sorry, drop them in the bin, not take them out of the bin. Okay, you can go watch the video slower at your leisure. You have a quiz due tonight. You're thinking about your final project, and I will see you on Tuesday. Thank you.